Hi, in this video, we're going to go over preparing data for a regression supervised learning project. All right, so I'm not going to go into full depth on data prep. I've got plenty of videos on that. I taught data prep last semester. If you want to get into the nitty-gritty, get into the weeds of it, go check out that material. Here, this is just going to be a quick overview because what I'm going to do when I get to the modeling, I'm going to use this prepared data set to build my supervised models. Now, my data set is the House Prices Advanced Regression Techniques data set from Kaggle. It's a competition data set. And so, there's going to be some interesting, twists and turns as we work through this data. All right, so our goal is to predict the house prices from a particular data set. And so let's say that there's a new home that comes onto the market, and we want to figure out how much should what should be the asking price? What should I bid for that if I want to buy it? How much should I list it if I'm selling it? And so if I have this model, and I'm selling, what I can do is I can run the model and on my home and then raise the price from the predicted value. That way I know that I'm getting a good deal. And also I know how far I can come down before I'm actually getting a bad deal. If I'm buying a home, I can go through and run the model on a whole bunch of different homes. And then I can check to see, hey, which one of these are listed much lower than the predicted value. I want to check out those homes. All right, so let's first and foremost prepare our workstation. Now, I'm going to violate some principles in the tidyverse, and there would be a whole bunch of warnings getting spit out if I don't have that warn equals -1. And so here I'm putting as one of the options to not print out warning statements. The digits, this equals 2. This is to print fewer digits so that we don't get blasted in the face by numbers. And then SciPen, the larger the number, the more R wants to avoid scientific notation. Sometimes it just can't get around it. And here I'm just making sure I have no artifacts floating around. And I'm going to be using piping a lot on this one. I'm going to be using tidyverse techniques pretty extensively, but not 100%. All right, so let's go ahead and load our data. And so I got this from, okay, so there's something about this data set is that we've got a good number of categorical and ordinal variables for our predictor variables. And I don't want to go through and manually type out all the different levels. I'm lazy. I want to do this efficiently. So what I'm going to do, I'm going to use string techniques. I'm going to use text analytics to figure out what are the levels of each of the ordinal and categorical variables. And I'm going to extract it from the data description. And then I'm going to apply that straight to the data set. That way, for all my factors, I don't have to go through and individually type it out. I just get it out in one shot. This will make it easier to update the situation later down the road also. And it'll just save me some typing. All right, so here, this is the data description file. It gives a text file of all the different variables. So it gives all of the columns in the data set, numeric, categorical, ordinal, target variable, predictor, they're all here. So I looked at the format of the file and I figured out patterns in it, so I'll be able to extract only the categorical and ordinal variables. And then I'm going to set the levels of those factors using what I've extracted. And so had to read it in, so I used read file. Read file is kind of like the generic read it all in one, as like one long item, instead of don't read it as a data frame. Read it as one long item. And so then I have this really long character string. So then I split it up by new line, and then I look and I realize that Every time I have a column name, it's followed by a colon in this particular case. So then I use that to figure out what are the column names in the data sets. And then I build a data frame setting up what I'm going to have. So what we're going to do is I'm going to have the column names, and I'm going to have the different levels of the categorical variables and the ordinal variables on the second column. And so now here I'm going through and I'm extracting the part that I want. So here I'm getting the column name. And here, there are tabs in the data set. And this dot means any character at all, and the star means 0 or more times. So in this one, I'm looking for tabs, and then any character after it, and I'm trying to replace those with the empty character string to clean things up. And then here, I'm looking for things that are not column names. I'm deleting off everything from the colon on with here. And so you can see that now I have the column in the left-hand column, and I have, so here's the name of the categorical variable is on the left, and its levels are on the right. And so now I've got all nice and neat in a data frame. I'm going to use this so I don't have to type this out. I'm going to set up my data without having to do all the work. And you'll notice that I did not change the original data set from Kaggle at all. I used just really good text analytic techniques, string manipulation. All right, so now after I do that, I'm going to pull in my data. I've got a training data set and a test data set. This is a Kaggle competition data set. And when I do this, I'm using the readr package, read CSV. This is typically faster than base R. It's not as fast as data.table, but it's pretty fast. I find I prefer to use this over data.table. Data.table has its own syntax, but data.table is the fastest way to read data into R that I know of. Now, a problem with this that I ran into is that when R reads in that data, with the readr package, it's going to want to make sure that there's at least a certain level of syntactically correct aspects to the column names. I don't want that because I want to have perfect matching with that data frame that I established already. And so I set name repair to minimal. Typically, what I do in real life projects, I typically use the janitor function, make clean names. But here, I don't want the column names to be, improved. I don't want them to worry about, unique or anything like that. And so then I also create a train test column on there. And looking at this now, this line should have been above that line. I always like to have everything as a data frame, but the as.data frame should have been the last line of this piping. All right, now I'm going to do the same thing that I did with train, but now I'm going to apply it to the test set. The difference here is that I'm going to have a column for my target variable. It's the test set. I don't know what it is. So I'm just going to put in A for blank. And when I create the train test value, it's going to be equal to test. And then everything else will be the same. I'm going to stack the train and test data set on top of each other on this step. And I'm going to convert my target variable to numeric. You'll notice that when I read everything in, I read everything in as a character. I like to read everything in as a character when I first look at things. If I'm doing a SQL query, typically what will happen is whatever is in the database is how it's coming out to me. But when I'm reading from a flat file, I like to read things as a character to make sure I don't lose like leading zeros off of ID numbers or anything like that. Now, as I work through this, I realize that pool area is virtually 0 100% of the time. It's not 100% 0, but it's so close, I felt like it just isn't even worth including in the data. So I went ahead and kicked it out with a select statement. All right, now on the next thing I did was I filled in missing values for my categorical data. So when I do this, I'm actually imposing a new level upon my categorical data. And so what we're going to end up doing is I'm just going to go through, and anytime I have a missing value, I'm going to replace it with NA. Now, I looked through the data and I realized that there's NA for missing values on some of the levels. Now, I could have left it, but I've had experience with stakeholders where NA, they'll be like, is that North America? You know, I don't understand what's going on. If I do N/A, so different. N/A, that's how Excel presents some missing values. And so more people are familiar with the N/A, so I'm going to put that in for my missing value level. Now on this step, I'm going to go through and I'm going to establish what the different levels are of my categorical predictor variables. And you'll notice I'm just going down the line. I'm going through all of the different columns that I have in there, that left-hand column of that data frame, and I'm using it to set up what the levels are. Now, something I also did, I found that data description doesn't have all of them. It doesn't have all the levels. There are a few that are in there that aren't in. There's a few levels in the data set that's not in the data description. Also, N/A isn't in there either. And so you'll notice that I set it up so that I've got all of the levels that are in the data description, plus I tacked on all the levels that are in the data that's not in the data description. I put those at the end of the levels. And I spot checked it afterwards, and that was a good call on my part. Now for my numeric predictors, first and foremost, I convert them over to numeric values. I load them as character. Now I'm converting them to numeric. All right, so now I've just got my data loaded onto my workspace, and it's time for me to start actually visualizing. So first and foremost, I want to better understand my data. I want some insight into what to do during my modeling process and in my data prep process. And I want to be able to show something to my stakeholders to show them that I know what's going on. You can trust what I'm doing. My models are safe to buy, and visualizations are a great way to do this. So something that I like to do is when I have a regression problem, I like to color 1/3 of my points, let's say red, 1/3 green, 1/3 blue, or some other colors like that in my visualizations to help me understand what's going on when I look at them. So I went through and binned my target variable into 3 different buckets, and I'm going to use that to establish the colors on what's going to happen on my upcoming visualizations. Now, something I always do when I do my visualizations is that I always give it a title. Personally, I say, here I'm saying histogram of sale price. I say exactly what the object is. If it's a bar plot, I say bar plot. Box plot, I say box plot. Why do I do that? Well, let's say my stakeholders aren't real comfortable with what they're looking at. Let's say that they've never really seen a histogram. Maybe they question it. Maybe they don't trust it when they're looking at my PowerPoint slides. They can look up histogram. They see on Google that it's a legit thing and it's a normal part of data science. They're going to feel more comfortable with me going down the road. So I set it up so that they can verify my work. Now here, something I always do is in my subtitle, I try to point out things that I want my stakeholders to see. I want them to notice. I want them to realize. And here we're going to have some skewness. Also, I'm saying each color has 33% of the data. That's actually only approximately 33%, but I thought it was okay. And then something that I find is a really good best practice is to put your data source in your visualization, because you're going to have this experience where someone's going to go like, hey, how'd you get that? I got the data right here. I can show my code. I can explain every step to you. But when you don't show your data source, your stakeholders may expect the data to look differently because they have experience with similar but different data. And in that situation, your stakeholder is not thinking about the results you're sharing. They're thinking about, like, why is it this way instead of the way I expected. You always want to avoid that thought process. You want things to be, you always want to be leading your stakeholders to the conclusions you're trying to give them. All right, so now here's our histogram, and notice that the colors make it easier to kind of see, like, where's the bulk of our data, where's the biggest concentration of it, and we notice that we've got some skew rightness going on off of this. Okay, so what I can do, I can apply a Box-Cox transform to make this a more symmetric distribution. All right, so now I'm going to be transforming the data, but it's an invertible transform. It was approximately negative 0.1. And what I can do is I do this transform now. After I get my predictions to convert back, I do the inverse of the Box-Cox transform to get the actual value I want. And frequently, this can greatly improve your modeling. And so you'll notice that the histogram is closer to symmetric after I apply the Box-Cox transform. And you'll notice that the scale has drastically changed by a lot when I did this. All right, so now let's visualize our target variable and our categorical predictors. All right, so what we're going to do here is I'm going to set up, I'm going to have box plots. And so I have a numeric target variable and I have categorical predictor variables. So what I'm going to do along the x-axis is going to correspond to the categorical predictor variable. The vertical axis will correspond to my numeric target variable. Now, something that I strongly recommend to you is that you figure out which visualizations are the most compelling before you show them to your stakeholders. So what I like to do at work is I will figure out an order of, like, most informative predictor variable to least informative, and I'm going to show the first one and then the second one and the third. And at a certain point in my presentation, I stop showing, and I'm not going to show the least informative predictor variables. And I find that this is good practice, because if you show things to your stakeholders that doesn't inspire confidence, that doesn't really add to the conversation, you're wasting your time. Where I work, I have to display visualizations like we're going to see in a moment, and I have to basically make a PowerPoint slide for my stakeholders to look at. Now, I'm going to give them the entire PowerPoint slides, but during my presentation, I only show the first ones. And then it's like, oh, well, we have a whole bunch of visualizations, yada, yada, yada. We skip the ones that I don't want them to see. And so how I'm going to order these, I'm going to use code. I'm going to do a Wilcoxon signed rank test to achieve this. And so here, what I'm going to do is I'm going to take a look at all of the different levels of a predictor variable, and I'm going to look at their central tendencies. Do these have different central tendencies? You can think t-test. I use Wilcoxon signed rank test instead of the t-test. T-test would have worked, but I find that you tend to get artificially small p-values when you do a t-test, because the t-test has greater power than a non-parametric test. So what I'm going to do, I'm going to do pairwise Wilcoxon signed rank test. And then here, I'm going to take the average of all the p-values. Now, there isn't really a good justification for that, but I find that this is a good way to just figure out where does it look like I have a better categorical predictor than others. And then I'm going, in the order that I get from this, from smallest p-value to largest p-value, average p-value that is, I'm going to present the visualizations like that. And so here, in our box plots, what we want to see for a good predictor is where the boxes look like this. The boxes have very different vertical position. When they're like this, they're next to each other, they're not informative for the target variable. What I want to see a big difference in the boxes. I want the boxes horizontally, cutting across to not overlap at all. And so by the Wilcoxon-Sign-Rank criteria that I set up, this is the most informative predictor variable I have of central error. Okay, that's kind of surprising. Of all my predictor variables, central error is the one that's most informative. Yeah. But look at the difference in the range of values, how we get like so much larger value up here than here for the maximum. Now, next one is garage finish. And you can see that between fin and missing, there is, a difference between those boxes. And when we get to kitchen quality, we can see a big difference between extremely or excellent and fair. Exterior quality, all right, exterior quality, that makes sense for higher values, be important. Now paved drive, now we don't see as much of a difference. And as I keep on going down the list, we're going to see more and more that there's going to be less of a distinction between the boxes. Also, something that I do, I'm coloring by the median value. That helps me visually see distinct differences between the boxes. So the boxes are filled in by their median value, and here's the median sale price. And you can see that the boxes are starting horizontally to get more in line with each other. You just keep on, there's a little bit of difference here. But, we just keep on scrolling down and we can just, see how it goes. Also, sample size is having an impact on the p-values. So the box plots aren't telling you the full story. I could have gone wider or more narrow for the box plots. Stakeholders generally don't like box plots in the first place, so I usually don't worry about the width to set this up. But as we keep on scrolling down, we just see more and more. And at this point, I would not be showing these to my stakeholders if I didn't have to. If they ask, oh, well, what about a particular variable, then yeah, I will definitely show that to them. Yeah, so what in these visualizations, we want to see boxes of different vertical position and very distinct colors to make them more informative. All right, I'm going to scroll past all of these. And yeah, so we're all done with all of that. All right, so now the next thing I'm going to do is I'm going to make sure that I don't have anything that's too extreme in my numeric values. And so what I'm doing here is I'm going to look at the 99th percentile of the data. Any value greater than the 99th percentile, I'm going to mute it down to that 99th percentile value. I'm going to find the 1% value. So I'm going to find the value where 1% of the data is less than or equal to it. All the values less than that cutoff, I'm changing to the 1% value. And so what this does, this helps prevent outliers from pulling my model away from the rest of the data. Now, the next thing I'm going to do with my numeric variables is I'm going to apply the Box-Cox, the Yo-Johnson, and exponential transforms. All right, so these are all related to each other. Box-Cox cannot take 0 or negative values. Yo-Johnson can take some zeros. Exponential transformation, I've never had success with this, but that is an option. Box-Cox, I find, is the best choice of these. If that doesn't work out, Yo-Johnson is my second choice in exponential transformation. I only use that when I'm just having trouble getting things to be transformed the way I wanted. So what I did was each individual predictor variable, it's numeric, I considered the Box-Cox transformation. If it looked good, it got a Box-Cox transformation. If it didn't, I considered the Yo-Johnson. If the Yo-Johnson transformation looked good, it got that transformation. If Yo-Johnson did not look good, then I tried the exponential transform. If that looked good, went with it. Otherwise, there were no transformations for that particular predictor variable. And that was my scheme. Box-Cox is the most simple of all of these, and it has some nice theoretical results related to limits and logarithms. And so I did before filming the video, I did exploration. And I figured out which ones should be transformed in each way. It worked out, in my opinion, none of the variables should have received the exponential transform. And so here are the ones that we have for Box-Cox transform. Here are the ones that Box-Cox didn't look that great for them, or it just didn't run because of zeros or maybe negative values. And so then I tried Yo-Johnson and it looked good. And then the rest, I just left as is. I didn't transform, I didn't change anything. Another option would be to bin my numeric predictor variables. I prefer to not bin my numeric values. That's just a personal preference. And so how to achieve this, to make sure that things went exactly the way I wanted it to, I specified what predictor variables to be transformed, and I put it into the caret preprocess function with only the one method involved. And so I did the same thing for Yo-Johnson, preprocess function from caret, and I said only this one method. Now, the way that the preprocess function works is that you have to specify, or you have to run the predict function to be able to get the actual transform values. The reason why the caret package does this is that we fit a preprocess function, then down the road, we get new data. I need to make a prediction on it. I first put it into preprocess, then I put that output into my model. I could have also centered and scaled. I could have also done imputation. I chose not to do either one of these here. I really don't like the preprocesses function, its version of imputation. It's got tree, it's got k nearest neighbor, it's got median. I've never felt satisfied when I've dug into the output, honestly. All right, so now let's go through and visualize our numeric target variables along with let's visualize our target variable with the numeric predictors. Okay, so once again, I want the most informative predictor variables first. I want the least informative predictor variables last. So what I'm going to do is I'm going to compute the correlation between my target variable and each individual predictor variable. Now, I'm planning on doing more exotic models than just linear regression. So I'm going to use Spearman correlation instead of Pearson correlation. Pearson correlation is what I would use if I was 100% guaranteed to be doing a linear regression model. But I'm going to be having more flexibility down the road. So I want a more flexible correlation. I'm using Spearman. Spearman is this isn't 100% correct, but a good way to think of it is that Spearman's correlation does Pearson correlation, classic correlation, on the rank of the values instead of the actual raw values. It's better at detecting monotonic, nonlinear relationships than Pearson. And here I'm using all the pairwise complete observations. Now, if I need a positive definite or semi-positive definite matrix for a theoretical reason, this is not a good choice for what to use. You want just complete cases, but that's not an issue in machine learning. It's usually more a classical statistics problem. And so I'm going to get a correlation. Yeah, so we get correlation going, and I'm going to go through and I'm going to order things from largest absolute value to smallest absolute value. And then I'm going to do something similar to what I did before, in that I'm going to put in a title. Notice that I'm taking, the scatter plot of sale price by predictor variable. I'm using the paste function to achieve that. I'm putting in the Spearman correlation, and I'm indicating that each color has about 1/3 of the points. And I indicate my data source. I'm doing a scatter plot, so I'm just putting down the dots. I'm going to put a lowest curve over my dots. I could have done a generalized additive model. I could have done a linear regression model. I chose lowest. Generalized additive model didn't work for all the different predictor variables, and the LM method, the linear model one, I feel like linear regression is too rigid for the more flexible model structure, so I'm using lowest. Typically, I prefer to use this generalized additive model, GAM. All right, so we can see that this predictor variable has a 0.73 Spearman correlation with our target variable. And we can see the colors. Now, one thing that's nice about putting in the colors like this, 1/3 of the dots are red, 1/3 of the dots are green, 1/3 of the dots are blue, approximately. All right, so here, when I see that the green dots are here, I know that I have a lot of overlapping dots. Look at how big the blue region is. Look at how big the red region is. In terms of dots, there's an equal number of dots. And so I know that I've got more dots here than visually I can see because they're stacked on top of each other. Another option I could have gone with is I could have induced some transparency, so I could have been able to visually see where do we have more concentration and less. I didn't want to get too complicated, so I didn't do that. All right, so next we have a 0.69 correlation. And this looks like I could have just had a linear regression model passing through. Next one is 0.65. Notice the clumping that we have going on here. 0.65. All right, so when you get less than 0.7, the utility typically isn't so great. So now, you know, when I get below 0.6, it's going to be, you know, the predictor variable is going to be less useful. And you'll notice that most of this here, most of the line is flat. Like there's no, like here, it looks like, practically speaking, this is a flat line, meaning there's no meaningful relationship with the individual values on this range and my target variable. And we have a little bit of incline over here. This one's looking a little bit better than that. And, you know, we just have a bunch of visualizations to go through. And the ones that were transformed by Boxcox or Yo Johnson, in the visualization, they are the post-transformed version. Before making the video, I actually went with both of them to check it out. Yeah, here we have a correlation of less than 0.3. You know, like that, you know, this is just a flat line. There's nothing going on. It's unlikely that these last predictor variables are going to be useful. So I'm probably going to end up kicking these out when I do my feature selection. Yeah, so look here, look how flat that line is. There's, you know, practically no relationship between years sold and the transformed version of the sale price, which is kind of surprising because I thought inflation would be involved. Oh, well, we've got the 2008 data in here, so you know, maybe, yeah, it's interesting that we have pre 2008, post 2008. But yeah, so I didn't catch that when I was preparing for the video. The visualization helped me find something out. So when I'm doing my modeling, I would strongly consider pre and post financial crisis prices. All right, so now I want to fill in the missing values. I could eat, and now here we already took care of the categorical by making the N8 level. Now I want to worry about the missing values of my numeric predictors. I could have done this using the pre-processed function, which would definitely have some advantages over what I'm going to do, but I chose to use the misRanger package. The reason why I did this is I have my train and my test data set together. And so when I impute, I only need to impute one time. If I had to build a model and then let's say month after month, week after week, day after day, something like that, I have new data coming in, the misRanger function isn't going to be a great choice. Why? Because it doesn't give me a function to work with. In the situation like this, every time I want to use misRanger or a function from the mice package, I have to refit every single time to impute. if I was to use the pre-process function that we looked at a moment ago for Box Cox and Yo Johnson, that gives me a function. So if I tell it to do imputation, what it will do is I save that function, I get new data, I put new data in the function, boom, I don't have to refit anything. And I have consistency. If I'm refitting my imputation model every time, I have a different imputation model every time. So it's not a great choice. But for this project, this video, it's okay. And so here are the variables that are being imputed. We have one or more missing values in here. All of these are the variables that are being used to impute. And we have some iterations that are going on. So it ran through 3 iterations. A sign that you have a good model is that things converge rather quickly. And so if it took 100 iterations to finish imputation, that's a sign that I didn't really have a good imputation model going on. Oh, I also told it to return the out of bag error, which can give me an indication of, this is similar to a validation set or a test set to let me know, do I have a good model on my hands? Now, I'm going to want to run association analysis. So when I say association analysis, think correlation. All right, so what I'm going to do when I'm going through feature selection, I want to go through and make sure that I have the, I keep informative predictors, and I kick out things that are highly correlated with other variables. So if I had 2 variables that are highly correlated, having both of them is redundant. I want to keep the best one, kick out the other one. And I'm going to use this correlation analysis to achieve this. Now, when I deal with categorical data, I can't do correlation. What I'm going to do is Cramer's V. I'm going to use Cramer's V as like a pseudo correlation, and it's on from 0 to 1. It's derived from the chi-square test, and we're going to use that as a way to basically treat it the same as a correlation number and proceed. And so now I've got my correlation plots. I had trouble with that pool column, and I commented out this part. I should not have commented out for this. After I figured out that the pool column was the issue, I should have put it on H class. So what would happen if there was H class was here? It would take hierarchical clustering on the variables, and I would be able to see like rectangles, or excuse me, squares of variables that are highly correlated with each other. And that gives me an indication of who's correlated with each other. And if I kick one out, who has the ability to pick up the slack when I do my feature selection. Now here's my correlation plot. Now here you'll notice I've got those squares going on. So this indicates, this square, that if I was to get rid of one of these predictor variables, the other ones in the square would pick up that slack. Same here. And here we have, strong relationship, but we don't have a full proper square, but we can identify highly correlated variables. So if I kick out one, I can keep the other one to pick up the slack of losing the first one. Now I'm going to perform variable clustering. So when I do Ward's D, Ward's D does a good job of giving me more even groups, while single linkage does a good job of identifying outliers. So here, this is showing that year sold is very different from all of the other predictor variables. Since it's very different than all the other predictor variables, I'm probably not going to throw that out, even if it doesn't look very informative, because there's no other predictor variable that's going to pick up the slack if I kick it out. When I look at Ward's D, I can see that, like this predictor variable and this are highly correlated with each other. I'm using correlated like more loosely with this, more colloquially. That if I get rid of this one, the other one is probably going to be able to pick up the slack of losing that predictor variable. And you can go down the list and find the pairs to make sure that when you're doing your feature selection, removing predictor variables, you try to keep the ones that would not have another predictor variable to fill in the gap. Now here's the same thing on the categorical data. Here's using Ward's D. So we can see that external quality and overall quality look very similar to each other. That's not surprising. And here I've got my single linkage. We can see that fence is distinct from all other predictor variables. Kind of interesting. All right, so now let's go ahead and prepare the categorical and ordinal predictor variables. All right, so in my first run of building my model, something that I will do is I will take my categorical and ordinal predictor variables and I'll bend them into two levels. Why do I do that? Well, let's say that I have states as a predictor variable. Well, if there's 50 states in my dummy variable representation, I'm going to have 49 or 50 predictor variables. They're all going to be binary. And so the more predictor variables I have, the more prone to overfitting I am. Okay, so I don't want a lot. Also, if I only have one predictor variable for it, you'll notice that I'm able to figure out a variable's like correlation with others, or association with others. I can identify, it's easier to do variable clustering on a binary bin column instead of the original version. And also, so it makes interpretation easier, and especially when we start getting into variable importance, that if I only have like one dummy variable for a categorical predictor variable, feature importance is very easy to figure out. Variable clustering, I can pretend it's a numeric value. I have a lot more flexibility in choosing this, and I'm not exposing myself to overfitting. So what I typically do in real life for an actual project is I first go around, I set up my data where categorical and ordinal are binned into approximately 50-50 binary columns. Then I run through my feature selection process. I see which ones look like they're informative. Then I take a step back and I reevaluate the binning. Is there a better binning off of this? Yes or no? Maybe, maybe not. It's a case-by-case judgment call. And then I proceed with my project of building models. And so I've got two ways to bin things. First one, I'm going to call it the other technique. In the other technique, we have a very large percentage level. And we're going to take all of the other levels and just call it other. And so we've got basically, we have all the other ones and then the not other one, the big mamma jamma. The other technique is to look at the average of our target variable by the individual groups of my predictor variable. And I'm going to call that the conditional means. And so I'm going to take, let's say, the first level of my the first predictor variable. I take the corresponding average of my target variables off of that. And then I go to the second level, take the average of target variable, third level, and so on. And then I'm going to look at which levels have the largest average, which ones have the lowest average, then bin them together. All right, so grouping into the other category, what I'm going to do, you see I have a table. All right, so central error, 2 levels, not changing anything. Then paved drive, you see that 90% have a paved drive. So I'm going to put no and P together. 60% are in the basement exposure of no. All the other ones I'm going to put into a common level. And so you'll notice that when I do this, things get a little bit, it'll be closer to 50-50, as close to 50-50 as I can possibly get off of these. Here, almost 90% are TA. I'm putting all the others into one group. And I'm just going to keep on doing this and keep on rolling on down. And you'll notice that on all of these that I chose to do the other technique on have proportionately a large singular level. When everything's more even out for the percentage for each level, it's a better idea to group by the conditional average. And so the group by the conditional average, this one's a little bit trickier to implement, to identify. What I'm going to do is I'm going to take the levels that I have. So this one, garage finish, is the categorical variable. Here are the different levels. I'm going to sort the levels by the average target variable. I'm going to take the number in each of these. The number of NAs is 159. The unfinished is over 1200. Some kind of finishing, our finishing is over 800, and then finished is 719. Okay, and so here's that proportion. What I'm going to do, I'm going to add these proportions going from top to bottom. And that gives me this cumulative sum ascending. Now, I'm going to add these proportions going from bottom to top, but I'm going to take that value and subtract it from 1. And then I'm going to take the average of these two, and then I'm going to, and this is how I'm going to set up the cutoffs. So here I'm going to set up the cutoff as 50-50 because I want 2 levels. If I wanted 3 levels, I would do 1/3, 2/3. If I wanted 4 levels, I would go 25, 50, 75 for the cutoffs. My supervisor at work likes the 1/3, 2/3 cutoffs, by the way. And so here I can see that unfinished and NA are going to go into one group, and the 2 ones that are finished go into another one. Okay. Kitchen quality, I'm doing the same trick that I'm doing. Notice that if I take this number, that's here. If I add these 2 together, that's this. There is rounding going off. If I add these 3 together, that's this number. If I add these 4, remember there is rounding, that's this number. If I add all of these, it's that number. Here, I'm taking 1 minus this value, that's 1. 1 minus these 2 added together is this value. 1 minus these 3 added together is this. 1 minus these 4 added together is this. 1 minus all of these added together is this value. And so I find this is a good way to go. Now, why do I have to do this in 2 directions? Because when I have a large, proportionally large level in the middle, it can change how the binning happens. And I find that this average of the 2 cumulative sums is the best way to go. All right, so now that I've gone through and I've binned all of my predictor variables, I've done my Box-Cox transformation, I've done my Yo-Johnson, I've imputed missing values. I just want to double check to make sure everything looks good, looks about right. So, when I did my binary binning, I'm going to have minimum, first quartile, median, third quartile, and max will all be 0s and 1s. Now, it's possible to get like a 0.5 on the first quartile, median, or third quartile. The mean is actually going to be what's more interesting to us when we have our binary predictor variables. And just go through, make sure things look all right. All right, so year built, this is post transformation. Those numbers don't make sense. Remember that many of these were transformed, and because of that, some of the values look off. All right. So the next thing after that is to save it so I can use it. At work, I would store it into a proper database. All right, so your homework is to take your data set that you picked for your regression models and do your data prep. You don't have to use the techniques I used, but you want to do the best data prep that you can. Your data prep is going to be what makes or breaks your models. Your model structure is not as important as your data prep, and your parameter tuning is not as important as your model structure. And so data prep is the most important step for us in this situation for this class, because we're not involved in data collection or selecting data. we're just, we're finding a spreadsheet online for our homework and then we're working on it. So your data prep is going to be critical to building good models. Take your time. This is important. If you screw this up, it's gonna hurt later down the road. Do good, solid data prep on this. All right, well, that's all I've got for you. Life is short. Do math.